What does it say? Yes. Oh. That's the non-trivial one. We'll get there. We will get there. Because by and large, right now, I'm pretty sure people are working on the trivial explanation. So, what's the trivial explanation of Newton's? Like, what do you think it says? Yes?
So basically, if we were to throw a ball in space, it would just keep going like that. But if we throw it here, where there's gravity as a force,
Okay.
when we throw it up, it slows down because that's the external force acting.
So, in other words, what Anna's saying is that if you're in an environment that is free of any external force, and an object is in motion, meaning it's moving at a constant velocity, not necessarily a constant speed, what will it do? It will stay at that constant velocity. Or in other words, if you were to actually write that down, what that implies is V equals C, in other words, constant velocity, implies net F equals, no, net force is 0. Or, vice versa, net force equals 0 implies that the velocity is constant. And notice, can that constant be 0? Yes. So, let's see if we can see the consequences of this trivial view of Newton's first law. Notice I'm saying this is still the trivial view, because it's not obvious that this is true at all. Does this conform with our experience, yes or no? In other words, do you see objects do this? No. You don't see objects do this. In fact, it's highly unusual if you ever see an object do this. Yeah, okay, air hockey. Think about what's required to make that environment. But imagine that you're Galileo, who thought of this law. This is Galileo's law. A little heads up. The whole last unit was Galileo. None of it was Newton. You'll see. You'll see the answer to that question as we go in this course. The answer is it's just getting more complex. So here, I'm going to tie this. Zaid Khalil, the average genius. Yes. No. That's it. Thomas, right? Wait, Tom, yeah. That's what these guys said. Now it's funny. One of the theorems that I prove to my APC students, it's called the Shell theorem. It was done by Newton in his Principia, and I remember the first time I saw it. I was I think either a sophomore. I think it was a sophomore in college. And because I wasn't smart. I wasn't taking AP Physics as my first physics course. You'd have to be crazy to do that. So yeah, I saw the proof of the Shell theorem. I was a physics major. And I was like, you know what? Zaid Khalil is just not going to be making a contribution to science. That was because realize I saw this, and this was done by someone 500 years ago, and it was so far beyond anything that I thought I could be capable of. So, all right, so now here's a question. Here's a ball. What does Newton's first law mean?
I don't want to stay there.
Okay, so in other words, if I pull on this, what do you expect to happen?
We're going to stay.
You expect it to stay there? Which string will break? Which string will break?
The bottom one.
Ah, which one is it? Which string is going to break? Ready? 1, 2, 3. So, why? Because I applied an impulse force. And what that impulse force did, it only acted for a very brief moment on this system. And this thing is called an inertial ball. It's enormous. Want to feel it? Lift it up. Okay. He's just so strong. So, it's very massive. And what is this thing at? It's at rest. And it wants to stay there. So I apply this very quick force. And what happens as a result? It stays there because the impulse force basically only acts on the string. This effectively is a wall relative to the mass of the string. So how would I break this top string? That's right. Exactly. It's a physics class. Come on. You think I'd wear sneakers that look like this for no reason? They're not steel-toe boots, but they don't slip. So you apply a constant pressure or a constant force, and what ends up happening is now this ball becomes part of your hand ball system. And now the weight and my hand apply a force on this top string that breaks it. Notice there are different types of forces. One was just an impulse force that just sheared that bottom string. So this is a physical illustration of Newton's first law. But yet again, this is the trivial illustration. This is a trivial view of Newton's first law. Now I want to get to the non-trivial view. And the non-trivial view of Newton's first law is not trivial. In order to actually illustrate it, because what it really says is that, and this is strange, like an object in motion stays in motion, an object in rest stays at rest unless acted on by an external force. What that really says is this. Newton's laws of motion are only valid in inertial reference frames. What? How's that even, how are they even consistent? So let's see what this means. So what I have here is I have a nice setup of cars. I've got Darth Vader in a red car. I've got Albert Einstein in the blue car. And I've got Stephen Hawking in his hella chair. All right? So, and I need all three of them to be here. And so what I'm going to do is, at first, I'm going to investigate constant velocity motion. So which direction do you want to call positive? Okay, so Albert Einstein's going at positive 20 meters per second, and this is like a traffic light. And Darth Vader is going negative 10 meters per second. Meaning he's going which direction? That direction. So, and they're going at constant velocities. So, Albert Einstein looks at Darth Vader's car coming, and he says, oh, let me give him a call. Because, of course, that's illegal, but when you're Albert Einstein, it doesn't matter. So, he gives Darth Vader a call, and he asks him, first he tells him, Darth, I see you're coming at me at what velocity is he coming at him? Be careful. He's coming at him at negative, be careful, negative 30. Darth Vader's going negative 10. Einstein's going positive 20. So that means Einstein observes him going negative 30. If he was going positive 10, that means he would be traveling that way. Oh, okay. So he observes Darth Vader traveling at negative 30 meters per second, constant velocity. So naturally, what does he ask him? He asks him, do you feel force? And Darth Vader says what? What will Darth Vader say? What will he say? He'll say, no, I don't feel anything, man. I don't feel force. I'm traveling at a constant velocity. Darth Vader looks at him and says, you know what? I see you coming at me at what velocity? 30 meters per second. And you're at a constant velocity. Do you feel force? And Einstein says, no. And just to verify things, they both call Stephen Hawking, right? Who's at rest at the red light. And what does Hawking observe? Hawking observes Darth Vader going at negative 10 meters per second, constant velocity, and Albert Einstein going 20 meters per second, constant velocity, right? And he asks them, do you guys feel force? They both say no. They ask him. They say, I see you coming at me at 10 meters per second. And Einstein sees him coming at him negative 20 meters per second. Do you feel force? No. None of them feel force. They're all moving at constant velocities. We're good. Next day comes. Totally different day. Okay? They come up to the same intersection, but it's a different set of circumstances. In this set of circumstances, Stephen Hawking is at a red that he has to make a left. So it's, what is it? Left turn green. Do you know what I'm talking about? Like when the arrow. So you have to wait on the arrow. Albert Einstein, so right now, he has a red light. He has a red light. He has a red light, but he's coming in from behind. And he's anticipating that this light's going to turn green. All right, so that means he's moving at a constant velocity. Let's say his velocity was 20 meters per second. This is Einstein. Hawking's at rest. Darth Vader's at rest. What happens? All of a sudden, the light turns green for both of these guys. So, what happens? Darth Vader begins accelerating. So Darth Vader accelerates an acceleration of 2 meters per second squared. He accelerates at 2 meters per second squared. Naturally, Albert Einstein's going to do what? He's going to call Vader. Actually, you know what? Let's hold off on Einstein. Hawking's going to call Vader. Okay? Because Hawking's at rest. So Hawking calls Vader, and he says, Darth, I see that you're accelerating towards me at, I guess this would be negative 2 meters per second squared. And he asks him, do you feel force? And what does Darth Vader say? Yes. Right? He feels a force. Right? Because when you hit the gas, do you feel a force? What force do you feel? Come on now. You've never been inside a car? Slam on the gas. What do you feel? You feel like you're being pushed backwards. Right? Is there a force pushing you backwards? We'll get to that in a second. Wait, is there a force pushing you backwards? We'll get to that in a second. All right. So, he asks him, do you feel force? Darth Vader says, yes, I feel force. But then Darth Vader gets tricky. He looks at Stephen Hawking. What does he observe? What does he see Stephen Hawking do? He sees Stephen Hawking accelerating towards him. And he asks Stephen Hawking, do you feel force? And Stephen Hawking says, I don't know what you're talking about, dude. I'm sitting here at a red light at rest. I don't feel anything. Okay? So what do? There you have a quandary now. Because both of them see the other accelerating, and they know Newton's first law, and they know that if you're accelerating, there should be a force. So who do they call up? They call up Einstein, who's traveling at a constant velocity. Okay? First Darth Vader, what does Darth Vader observe Einstein doing? He sees Einstein accelerating towards him, right? Similarly, what does Einstein see Darth Vader doing? Accelerating. So Einstein's going to ask Darth Vader, you're accelerating towards me. Do you feel force? Darth Vader says yes. Darth Vader asks him, because he sees him accelerating towards him, do you feel force? And he says, no. What does that imply? Who agrees with whom? Einstein and Hawking agree. Darth Vader does not agree. And this is what the real deep physical consequence of Newton's first law is. Newton's laws of motion specifies the boundary condition of the validity of Newton's laws. Newton's laws of motion are only valid in inertial reference frames. Period. Newton's laws of motion are only valid in inertial reference frames. I think you have it right in front of you, right? It's right in front of you. There's no need to write it down. Is it right in front of you? It's only valid in inertial reference frame. What's an inertial reference frame? It's a coordinate system that is moving at a constant velocity. So therefore, a non-inertial reference frame must be a reference frame that is moving in a it's an accelerated reference frame. Newton's laws of motion are not valid in an accelerated reference frame. Certainly not Newton's laws. So if you want to study physics, you go into an inertial reference frame. If you want to understand what's physically happening, you go into an inertial reference frame. So, for instance, you slam on the gas. What do you feel? You feel force. Is that force real? The answer is no. That force is not real. Why? Yes? Boom. Very good. When you're in the car, you're in the accelerated reference frame. In order to actually physically describe what's happening, what do you have to do? You have to step out of the car. So, for instance, take Einstein steals Darth Vader's car. You can do this when you're dead. Okay. So, what does Einstein feel when he hits the gas? Right? He feels nothing pushing him back. Right? He feels nothing. There's no physical thing that is pushing him into his seat. But when you step out of the vehicle, what do you observe? Step out. What's pushing Einstein? What part of the car? What part of the car is pushing on Einstein? The seat. So when you hit the gas, you're not being pushed back. The seat is pushing you forward. This is why forces is so conceptually difficult, because you have built up an intuition around non-inertial reference frames for which the laws of physics are not valid. So we need to step out of your experience to explain why this all works. Who did not get that? Please raise your hand. Okay, yes. Shoot.
You cannot explain anything in the non-inertial reference frame.
Not with Newton's laws, no.
Oh,
You need to modify Newton's laws.
like with other physics, you can explain.
But there are laws.
No, you need to step out of that non-inertial reference frame.
No, like without Newton's laws,
You need to step out of that inertial reference frame.
I think what he's saying is, are there different laws you can use if you're out of that?
You can modify Newton's laws so that they fit in non-inertial reference frames. Not a good idea, though. Yes?
So, like, does that only apply, like, do you ignore, like, the rotation of, like, the Earth, like, in the grand scheme of things?
Yes.
Like, that was given out of the
Very, very good. That is something that we're going to actually look at later in the course. Is the Earth an inertial reference frame? And the answer is approximately.
Wait, what?
It's approximately an inertial reference frame. And it's because the fact that your reference frame is rotating, and it's not rotating at a slow rate, I'd like to add. It's rotating pretty fast, but it's the acceleration that is caused due to that rotation is effectively zero for most of our purposes. If you want to sink a battleship, it's not zero. If you want to sink a battleship, you need to account for it. But if you don't want to sink a battleship, you don't need to worry about it. Do you understand what I'm talking about? You probably don't. What does it mean to sink a battleship? That means you're in, let's say, some naval battle, and there is some ship some distance away, and you want to sink that ship. You need to account for the fact that the Earth rotates in your ballistics to sink that ship. So the Earth is approximately an inertial reference frame. So, just to give you an idea of like what you would do, take this. I take an inclined plane. I have a cart going down it. The inclined plane is nailed. It's nailed into the desk. The desk is nailed to the floor. The floor is securely put on the earth. Okay? So what can you say about the inclined plane? It ain't moving. All right? So the whole point of this exercise, this inclined plane's not moving. It's an inertial reference frame. Okay? You can use Newton's laws of physics to describe the motion of this block along this inclined plane. Is everybody clear? You can go, in fact, you can use the plane as its own coordinate system. Why? Because it's inertial. It's not accelerating. So, what would be a situation where you can't? if this ramp was put on ice. Let's put the ramp on ice.
Okay.
What's going to happen now when this block slides down the ramp? The ramp is going to accelerate backwards. Now you can no longer put a coordinate system on the ramp. Why? Because the ramp is, it's moving at a non-constant velocity. It's accelerating. It's in a non-inertial reference frame. If you wanted to describe the motion of this, what would you have to do? Very good, Anna. You would set the table as your coordinate system, because that table's fixed now. Is everybody following this? Because this is a theoretical discussion. This is a discussion for your brain to interpret what's going to happen. Yes?
So what if while you were sliding the box on the ramp, what if the ramp was moving at a constant velocity? Like it wasn't
You're good.
still.
You're good. Constant velocity, you're good. But think about what mechanism that would be required for that. Yeah. What I'm saying is take that hypothetical thought, take it home, and think about the mechanism that would be required. Because it's not, I can't think about it on the spot right now. It will require several, it'll take me a while to think about how that would physically even happen. So, yeah, maybe it's on a conveyor belt. That's one. See, doesn't take much to be smarter than your physics teacher. So that's Newton's first law. We're done the first law. We're 1/3 of the way there. Yeah, we're 1/3 of the way to the final exam. So Newton's second law. I don't even need to modify this, because all I have to do is write second law. All right. Newton's second law is strangely one of the easier ones. But it's not. It's actually the one that you're probably going to be using the most. It's effectively an operational definition of what net force is. And what is net force? It's the mass of a body times the acceleration of the body. I have to be a little careful. Because what does this mean? This is actually, this is basically an operational definition of net force. Someone wanted to know, what is this vector net force? It is the mass times the acceleration of a body. I should probably talk to you guys a little bit about what a force actually is. Like, what is a force? Anyone? So, a force is something, yeah! Believe it or not, that is the right idea. A force is something you feel. And it's on a basic level, on the most basic level, it's a push or a pull. Now, there are some things that you have to be in contact with in order to exert a force. Like, for instance, that push. That's a contact force. Or you pull. That's another contact force. Force is a vector. It has direction. And it obeys something called the principle of superposition, which means you can add them. So there are non-contact forces. In other words, forces that are exerted on bodies that do not have to be in contact with the bodies. Can anyone name one? Yes. Gravity is the classic one. There are other non-contact forces. Yes. The electrostatic force is another. The magnetic force is a third. And there are other nuclear forces as well. Those are types of forces. So Newton's second law says that if you have a collection of forces acting on an object, that collection of forces behaves in such a way that if you observe the acceleration of the object, that if you know the quantity of the force and you observe the acceleration, that proportion is going to be constant and equal to something called the mass of an object. So now the question is, how do you measure that mass? How do you measure mass, guys? Come on now. You're juniors and seniors in high school. How would you measure mass? You use a balance. Everyone agree with that? And the answer is not necessarily. Because the mass that he's looking to measure is something called gravitational mass. This mass is called the inertial mass. And what the inertial mass is it is a body's resistance to a constant force. I need water, guys. I've hit the limit of what my throat can take. This man needs to stop talking. All right. Whatever. That's what cough drops are for. So, Mazel tov. So, so inertial mass, it is the resistance of a body to a constant force. It's the resistance of a body to accelerate under a constant force. What does that mean? Yes.
I feel like when you have the ball over there and the string, it looks like.
Yeah, but was I applying a constant force in both cases?
Oh no, sorry.
It's okay. This is not an obvious concept. Yes. That is gravitational mass. Yeah, it's hard to think of it as concept. It's not obvious. So I'm going to show you what inertial mass is. So, this is a cart. This is a fan. It's called a fan cart. So, bye. One of these days, I will get better. My voice will return to normal, and I will be back. Now, I was thinking that, I'm sure my students appreciate my dedication. And I thought, you know what, if I had stayed home, they would probably had an extra day to study. So maybe they don't appreciate my dedication. So anyhow, so let's see. Is this working? Now it is. So take a look. This is a fan cart. Is this applying a constant force? Yes or no? Why?
It's blowing air that way, which makes the cart.
Okay, so what does that mean? Why is that applying a constant force? Does that force depend? Get over here. Does that force depend on the amount of mass I put on it? Correct. The force I'm applying is constant no matter how much mass I put on this. So everybody follow this. Why? Because what's dictating the amount of force that's being applied? The rotation of the fan. What's controlling the rotation of the fan? Yeah, some battery that's totally external to everything else. So it's a whole externally powered mechanism. So I'm going to go. I'm going to turn this on. I need a helper. Thank you, Mr. Kramer.
What am I doing?
You're just helping.
Okay.
Help!
Oh,
Ah.
that helped.
Yes. So it's okay. It's okay. You'll be helping out some more. Come on, you're a smart guy. You're supposed to infer these things. And so you take a look, and what do I have? I have some mass, and I notice what's the acceleration on this, and what's its value? 0.152, right? And this is just the mass of the cart. So now what am I going to do? I'm going to add one of these blocks. You can let it go. And what's the slope now? 0.106. So this is mass of the cart plus one block. 0.1, say it out.
0.1067.
All right. So, got 2 on there. Let it go. And what is that? Is that right? Yeah, that's right. 0.095. It seems strange, but maybe not. I think this is off. Let me redo this. I'm going to let it go. Okay, 0.0868.
0.0868.
Okay. Add 3. Let it go. What is that? What? Nope. Let it go. .8084. Was it 808? So this is plus 3, and I'll probably end it with plus 4. Ah! I messed up. Put it back. That was my bad. I went to hit stop, but it stopped for me. Let it go. Oh, God. Put it back. Why stop? There you go. Wait. Let it go. And that's 0.062. So plus, was that how many blocks?
8.
All right, so now here's a question. We can turn it off, and thank you very much, sir. So now here's a question. What's the inertial mass? The inertial mass is the resistance of a body given a constant force to accelerating. That is the inertial mass of this body. Notice what happened when we piled on more and more mass? The acceleration declined. How did it decline? Less and less. Very good. Man. Wow. So decline less and less. Anybody know what type of graph she's actually thinking in her head? Right? So if you take a look, acceleration equals F over m. So what would this look like on an A versus m graph? Very good. That's called a hyperbola. So, the inertial mass is the resistance of a body to a force. And you don't measure it on a scale. But guess what? It's identically equal to the mass that you measure on a scale. It is identically equal to the mass that you measure on a scale. And so the natural question is, and the answer is, no clue. It's not, it is a postulate. Inertial mass equals gravitational mass. It's a postulate, and it is a postulate that we will verify in this class experimentally. But believe it or not, the person who really understood the full consequences of them being equal was this guy. And it was actually the equivalence of inertial mass to gravitational mass that led Einstein to his general theory of relativity. Yeah, and it's kind of sick. Like, he took them as equals, and he was like, all right, what are the consequences of the fact that these things, let's say they're equal. What are the consequences? And so notice, this was 300 years after Newton, that this very subtle thing that Newton knew about actually underlied a much broader theory. So the last thing I should say before you leave is Newton's third law. Every action, there is an equal and opposite reaction. But do you think I'll end class and say we're done with Newton's laws? No. Newton's third law is going to take a long time to internalize. Because really, it's the property of forces. If you were to actually talk about force as a vector, it is a vector with a definition, a boundary condition, and a property. Do you know what the difference between those things are? A boundary condition is the boundaries for what some type of equation or definition is. Hi.